This example is an application to two-dimensional motion, where it is shown here that a particle is moving in xy plane with an x motion having an equation of x equal 18t and a y motion with a position equals 4t minus 4.9t square, where all positions are measured in meters. The first part of the example, we need to write a position vector as a function of time in terms of unit vector notations. The second part is to find the average velocity in a certain time interval of t equals 0 to 2 seconds. And then in part C, an instantaneous velocity expression is required as a function of time, while in part D, you are asked to find the average acceleration in an interval of time from t 1 second to 3 seconds. And then finally, what is the acceleration of the particle? To find the position vector r in terms of unit vector notations I hat and j hat, it is written in this form: r as a vector equal x I hat plus y j hat. Knowing x equal 18t and y as 4t minus 4.9t square, you just insert these two equations into the vector notation in order to get the answer of the position vector r as a function of time. To get the average velocity as a vector, you have to find delta r, that is r final minus r initial, or you need to find its component delta x and delta y. To find that, you simply substitute the initial time t into the red equations x and y, or in the vector equation. You're going to get r initial, the vector position at t equals 0 equals to 0, where the final position, in order to get r final, you just substitute 2 into the same equation. You're going to get r final as 36 I hat minus 11.6 j hat. Then finding delta r is r final minus r initial, where r initial is 0. This means that delta r is equal to r final. And delta x is simply 36 meters. And delta y is minus 11.6 meters. Now, to find the average velocity, just divide the last equation of r final, which is delta r, by 2 seconds. You're going to get the answer of 18 I hat minus 5.8 j hat meter per second. To find the velocity vector as a function of time, we just write down the formula for the velocity vector, which is the derivative of the position vector r with respect to time. Then you can do that by using the x equation and dividing that with respect to time in order to get the component of the velocity vector along the x-axis. Similarly, we can get the component of velocity vector along the y-axis by taking the derivative of the y equation with respect to time. And doing that, we're going to get the first position vector equation as a function of time, where the I hat part represents the x component 18t, and the j hat part represents the y component of the velocity 4t minus 4.9t square. So this is the x component, which turns out to be constant, while the y component is a function of time. The velocity vector then finally has this form. Is obviously the velocity vector is depending on time, as the j component of the y component of the vector is a function of time, while the x component is constant. So in order to find the average acceleration, we can use this result of the velocity vector in order to have delta v along the x-axis and delta v along the y-axis. So to find delta v along the x-axis, initially, the initial velocity can be written as this, while as you can see that the x component is constant, doesn't change with time, while the y component, if you substitute in the above equation t equal 1, you're going to get minus 9.8 plus 4, that is minus 5.8. And that's why the j component has this number. Now for the final velocity, we're going to put in the same equation t equal 3. Obviously the x component is as is, doesn't change. It is not doesn't depend, because it doesn't depend on time, while the y component, if you put t equal 3 and multiply by 9.8, and then you have minus almost, if this is 10, it is minus 30. If you add that to 4, you get something around 26 or 25.4. This is the y component with a negative sign. Now delta x, obviously 0, because in the initial and final value the x component is the same, while delta y is minus 19.6 meter per second. Now applying the formula for the average velocity, you're going to get an answer of minus 9.8 j hat meter per second. That is the average velocity for in this example. And the answer can remind us with the acceleration due to gravity as well. To find the acceleration vector in terms of the unit vector notation, I hat and j hat, we simply take the last expression obtained for the component of the velocity vector along the x-axis and derive it with respect to time, or take the second derivative of the equation, position equation given in the problem, and with respect to time. Similarly, the y component can be obtained by taking the derivative of the x component of the velocity with respect to time, or the second derivative of the position vector with respect to time. And this is also can be obtained by taking right away the derivative of the velocity vector with respect to time from this equation in order to get an answer for the acceleration vector. As you can see, the x component of the acceleration is 0, while the y component is the whole vector component depends on it, which is equal to minus 9.8 j hat meter per second squared. This is obviously is the acceleration due to gravity. As you can see, the answer for instantaneous acceleration vector is similar to that for the average acceleration vector. This means that the motion is a uniform motion with a constant acceleration.
This toy bulldozer, which runs at a constant speed, will be used to show how velocities add together in 2 dimensions. The bulldozer is set on a paper sheet that can be pulled along the table at a constant velocity. The bulldozer is first set up to run directly across the sheet, and it follows this path. This time, the sheet will be pulled to the right at half the speed of the bulldozer. What will the path of the bulldozer be? The bulldozer moves at approximately 27 degrees to its previous path. What will the path be if the sheet is pulled at the same speed as the bulldozer? The bulldozer moves across at 45 degrees to its original path. If we now aim the bulldozer at 45 degrees to the left, how fast must the sheet be pulled to the right if we want the bulldozer to move straight across? Pulling the sheet to the right at approximately 7/10 of the bulldozer's speed makes the bulldozer move straight across.